Okay, so now we have encountered a number of different matrix norms. In particular, the Frobenius norm, the various p norms, special cases of the p norms 1 to infinity. Right? Let's not discuss the p norms in general because we have already argued that we're going to be using the 1 norm, the 2 norm, and the infinity norm. And let's now think about these different norms and how they fit into this picture that we painted earlier on. We had a category of norms that somehow linked the magnitude of A to the magnitude of the linear transformation. We said, well, there are norms that are easy to compute and there are norms that are differentiable. Let's go through it. Now, the Frobenius norm, if you think about it, is a norm that makes sense if you're given the matrix, but it's actually really hard to come up with a way of linking it back to the underlying linear transformation. So it doesn't belong here, but it is easy to compute and it is differentiable because it's the square root of the sum of the squares. So it belongs right here. Now what about the 1 norm? Well, the 1 norm we saw is easy to compute and it measures by how much A stretches a matrix, which is a notion that you can also link to a linear transformation. So therefore, the 1 norm belongs right here. It's not differentiable because the sum of absolute values is not differentiable. So it belongs right here. Similarly, the infinity norm belongs right there for the exact same reason. And then we get to the 2 norm, which again also can be used to evaluate the magnitude of a linear transformation because it measures by how much it stretches. So it belongs here. It is also differentiable because of the sum of the squares, square root of the sum of the squares that comes into the picture. But it's not easy to compute. We don't fully realize that until future weeks. So it actually belongs right here. And what do we notice? Every one of the norms that we have decided are important to us satisfy 2 out of the 3 conditions that we say are nice conditions to have about a norm. But none of them satisfy all. So, what are we going to be doing? We're going to be saying, we find ourselves in the following situation. We need to measure the magnitude of a matrix. What kind of norm makes sense in this situation? And then we pick and choose the one that satisfies the 2 out of the 3 conditions that we would like to have, properties that we would like to have about our norm, and then we go with that. And then, in our back pocket we have equivalence of norms, which tells us, well, if we pick a norm in a situation, then at the very least, if the matrix is large, it's large in all norms, or if it's small, it's in small in all norms.